practice. Oh, no, this is the wrong one. Let me double check, sorry. Okay, so can you see my screen with no problem?
Yes. Yep.
Okay, all right. So the first question, so for our final exam, so we have 5 questions in total, and each one is worthy of 10 points. So we have 50 points in total for the final exam, and we have another 50 points for the presentation, which we did in the morning. I think all of us earned some extra credit by asking and answering questions. So yeah, which is good. All right, let's look at the first one. So this one is easy, right? This one. Okay, so basically this is the data from a test cross, and this is the total number of the progeny from this cross. Okay, test cross, and we have 4. So here we want to analyze the genetic distance between 2 loci, right? A and B. So that B and L. So in this case, we have 4 different genotypes here. And the first one and the fourth one represented the parental type, and the 2 in the middle represented the recombinants, right? So this is what we are very familiar with. So if we got data like this, so what is the genetic distance between these 2 loci in Sally Morgan? So it's very straightforward, right? So we just divide this the number of the recombinant progeny by the total number of the progeny. So that's the Sally Morgan, the 10 Sally Morgan. Any questions here?
No.
Okay. And then, so based on that, so that means like R equals to 10 Sally Morgan, right? That R equals to 0.1, right? Okay. Now, the second part is to calculate the average number of crossing overs between these 2 loci using the Haldane map function. So I provided the function here. So of course you don't need this. you can find this equation in the textbook or in the lecture notes. And so here, so because the R equals to what in this situation? 0.1, right? So you just solve this equation. Solve this equation and find the solution for the x. So the x is the average number of the crossing over between these 2 loci, right? Does that
What
make
is the
sense?
unit here, Professor?
I'm sorry?
What is the unit for the x?
X is the number of the crossing over. So if you got 1, that means like the average crossing over between these 2 loci is 1. If you got like 0.1, that means like the average crossing over between these 2 loci is 0.1.
Okay.
Yeah.
Can I just because there is a log in this equation, so I just use.
Oh, yes.
I don't have to calculate the number, just show the equation, right?
Yeah. So yeah,
okay.
You just show the expression of x. That's fine.
X equals to something. Okay.
Yeah, but you have computer, so yeah, it's easy for you to get the number for me, right? Okay. All right. So the second question is, okay, so suppose we have 3 loci, so 3-point analysis. So very basic one, right? So we have 3 loci, A, B, C, and suppose these 3 loci are arranged in this way. This is the reality, the real way, how these 3 loci are located on a chromosome, right? And so So the first question is how many possible ways? So if you do not know the real arrangement, so suppose you do not know, we only knew the three loci are linked. They are on the same chromosome, but we do not know the real arrangement for these three. So how many possible ways for you
3.
to arrange? Yeah, 3 ways. So if you do
Right.
not consider the orientation, right? So there are 3 possible ways to put a unique letter in the middle. So that's why we have 3 ways. And okay, so briefly describe. So we don't need any calculation here. I just ask you to describe briefly how we can use this SAR, the sum of the adjacent R strategy to identify the optimal order of the 3 loci, right? So this is easy. Describe. Use your own language to describe. So first, you need to understand how this strategy works, right? And then you just explain that using your own language. Okay, I think yeah, the space is enough for you to describe. If not, so you can use the reverse page. So, oh yeah, so please, yeah. Let me think. Maybe I should send you the Microsoft doc, a Word document. So in that case, you don't have to print it out. So you can type in and save it and then send it to me when you are done. Is that okay?
Yes.
Okay. All right. So for some part like this, so if typing is not that easy for you, so you can grab a piece of scratch paper and write down your derivation, and then after you're done, you just take a picture using your phone and copy and paste that picture in this area. Include that picture in your answer, and then send it to me. Okay. So we do not need to talk about this, right? So I have shown this in the lecture notes. So how we can prove if the real order is like this, if these 3 loci are arranged in this way, so how can we prove that the SAR for the correct order will be the minimum, will be the smallest one, the minimum one. So given any wrong order, if you calculate the same thing, the sum of the adjacent R, so this value must be greater than the SR value for the correct order. So, do you want me to show this?
No.
Nope.
No. Okay. Good. Very good. So, okay. Now, so this is quick, right? So now everybody is expert, so I don't have to spend too much time on a single problem, so we can move forward very fast. Okay, so the second one. Suppose Z is the random variable to code the additive effects, A, and so here we just focus on the additive effects, so we do not worry about the dominance effect. So please calculate the variance of Z, so the variance of the Z variable for 4 different populations. So backcross, F2 real, and the doubled haploid. Any problems here? Any questions here? Because Z, right? So, okay, so if there is no segregation distortion, what does that mean? That means like if there's no selection force and everything is following the Hardy-Weinberg distribution, right? And if we are talking about a standard backcross F2, so in the backcross, we only have 2 possible genotypes. So A1A1 and A1A2, right? And then we only have like 1 and a 0. So the the proportion for the two genotypes should be 50% versus 50%. So with this information, you can easily calculate the variance of the Z, right? And for a standard F2, the same. Now for F2, we have 3 genotypes, 1, 0, -1, and the percentage, the proportion of these 3 genotypes should be 1/4, 1/2, and 1/4. So using the variance formula here, so you can easily calculate the variance of the Z, right? For the F2. The real is very similar for real, because the real population, we do not have heterozygous genotypes. We only have 2 genotypes, 1 and -1. And the proportion of these two is 1/2 versus 1/2. So it's easy to calculate the variance. The same for the DH, right? The doubled haploid. So any questions here? Good. All right, so discuss the difference between mapping, the QTL mapping using different populations, including this 4. So we have talked about this before, right? The backcross is not as efficient as F2. Why is that?
Because it has a small variance.
Yes. So because F2 has more information because we have 3 genotypes, right? And the variance of Z is larger, right?
Right.
So that means like, so this design is more efficient than backcross. Okay. Now, if we compare real and F2, what's the result?
Real has a higher resolution
Yes, because of what?
because of the accumulative generation
Very good,
information.
very good. How about the efficiency, like the variance of the Z?
It's higher than F2.
Yes, because if you calculate, so that's why, so I put the first part here. So once you calculate this, you can easily answer the second question, right?
Mm-hmm.
Yeah, the same for DH. So how about the comparison between DH and the real?
DH doesn't have higher resolution as RIL.
Yes, very good.
Mm-hmm.
But in terms of the variance of the Z, the same, right?
It's the same, right?
Yeah, okay, very good. Yeah, so this is what I want to see. So
Okay.
yeah, very good.
Okay.
And okay, so suppose now for this for F2 population, so we not only consider the additive effects, but we also consider the dominant effect, and we use W to code the random variable for the added. No, sorry, this is dominance. Sorry, typo. So I need to change this. So suppose we use W to as a random variable to code the dominant effect for D. So please prove that the covariance between Z and W equals to 0. That's easy, right?
Yep.
Okay. Very good. Okay, so now, the problem 3. Suppose we want to use a linear model to test a marker. So a marker, a single marker on the genome. And we want to see if this marker is associated with the phenotype of interest. So this is what we always talk about, right? So almost like half of this quarter, we talk about this. So how we can test we can use a linear model to test whether a specific locus, genomic locus, is associated with the trait. So suppose we use this linear model to test this locus, and write down the linear model for testing additive effects and the dominant effects. So just write down the model and describe the meaning for all the parameters here. Is that easy?
Yep.
Okay.
So we have 4 parameters, right?
So for this one, we have y equals to mu plus
D.
C A plus W D plus error. So which means we have mu, we have A, we have D. 3, yes.
And the variance?
Oh, the
Okay.
yes. So you are right. So we have to estimate the variance of the error. Yes, thank you. So let me think. So likelihood function. Okay. Yes. So we only have like 4 parameters, and once we got this, we can also estimate the variance for the estimation of the A and the variance of the estimation of D. Right? That's not the parameter, but that's what we can calculate for testing the additive effects and the dominant effects at any locus, right?
Mhm. Right.
Okay. And okay, so now you have, once you have the linear model, just describe how you can construct a test statistic to test these parameters using this diagram. So it's not that hard, right?
Mhm.
Just follow the strategy to describe how we can test whether this locus has a additive or a dominant effect with which contribute to the phenotype. Any questions here?
Do we need to use all the testing, like the weld test or the F test, or?
Just use one.
Okay.
Just use one. So and just describe it in a simple way. Do not write too much about the process. Just the major steps and follow this diagram and show how we can study from a hypothesis. So you need to start from a hypothesis, right? Yeah, that's the first step. And you need to end up with a conclusion step. Yep. So whether the p-value, so you're gonna show me, so if based on this test statistic, if we got a p-value greater than what, then we do what? If less than what, then we do what? Something like this. The steps. Okay.
So sorry, we basically say what we do, like describe our H0 as, and then based on the p-values, we either reject it or accept it. That's
right.
it?
Yes.
Okay,
yes.
thank you.
The process, yeah, sure. Okay, now, so because you are doing a statistical test, so definitely you may commit sometimes you may commit some errors, right, for the testing. So there are two types of errors, type 1 and type 2, and the power, and also the power that is statistical power that is associated with your test. Okay, now you need to define this definitions. You need to describe these definitions to me to make sure to convince me that you understand what these terms mean. Okay.
Can I just use like positive, false positive, or false negative, or I need to write down all the definitions?
So for example, if you say, okay, so type 1 error is
false positive?
Yeah, false positive. So then you have to define what false positive means, right? So
okay.
Use a simple language. Assume that I'm totally like I totally knew nothing about this. So try to use a very simple language to describe this concept to me. Okay. And you can use some diagrams. So do you remember? I usually use like 2 normal distribution and the area and the curve to show which one is the which one is which one is what. Yes. So just assume. So I knew nothing about this. Yeah, please use very simple language to explain.
So basically, for these 2 last parts, we don't have to do any calculation. We're just describing the like different scenarios that might happen.
Right.
Yeah. Okay.
No, you don't. So for example, even from the first 2 parts, you don't have to do any calculation, right?
Yeah.
Yeah. So just this descriptive. Yeah. Because I try to make the test as simple as possible. So, because calculation sometimes, so since right now it's a different, this time is quite different from my time when I was in school. So at that time we have to do the calculation because we do not have a powerful computer and a calculator. Right now, since you all have this kind of powerful computational tools, there's no point for us to spend too much time on calculating these numbers.
Yeah.
But as long as you know how to do this, that's enough.
Thank you.
Sure. Okay. All right. So here, suppose we are testing 10 markers at the same time. So suppose so this is a very simple genome. So we only have like 10 markers on the genome. And then we only want to test this 10 loci to see if any of them are associated with the traits. So in this case, we are dealing with the multiple comparison, right? Multiple comparison. Then, so how do we use the Baffaroni correction to help us to reduce the risk of committing enlarged type 1 errors in this multiple comparison? So here, you may need to do a little bit calculation right here. So you can say, okay, so the regular, so if we want to test a single marker, we use 0.05. But if we want to test the 10 markers simultaneously, what will be the adjusted p-value for each individual test to make sure the family-wise, the experiment-wise, type 1 error is still less than 0.05. Any questions here?
No. Nope.
Okay, good. Very good. All right, so problem 4. Suppose we are dealing with a F2 population and 3 genotypes here. And if we use this, and this to represent the genotypic value for the 3 genotypes, yeah, define the midpoint value, mu, additive effects, A, and the dominant effects, D, using the expression of these 3 values here. So you can use the diagram to show this, right? It's easy. Any questions? And so what is the difference between the broad sense heritability and the narrow sense heritability, and why we often use narrow sense heritability for the breeding program, for the selection program? Any questions here?
I have one for sure.
Huh?
I have one.
Yeah.
For this part, cause in the class you mentioned sometimes the dominance effect will mixed with the error environmental error. So usually we can only calculate the narrow sense heritability, right? But for the F2 design, so I think we can calculate the broad sense heritability.
Still, so this is tricky. So, so yeah, I put this question here in the practice test, but definitely I will not use this question in the final. But to answer this question, the easy way is to because for a progeny, so for any single progeny, so this progeny just inherited one set of alleles from mom, and another set of allele from father, right? So actually the inheritance unit is the allele, not the combination of the allele. So you just carry, I mean, inherit you. So for any progeny, so let me think. So the simplest way to answer this question is, okay, only the additive effect can be inherited through the allele to the progeny. So that's why. So we can use the linear model to accurately estimate the additive effect, but not the dominant effect. And the dominant effect is always confounded by with the environmental factors. So that's why. So when we do the breeding program or the selection program, we often consider the additive effects. That's why. So we only use the narrow sense heritability.
But in the F2 design, we can estimate the little d.
Yeah, we can estimate this, but in the selection program, in the breeding program, so when we want to so yes, you're right. So if we have an F2 population, we can estimate everything, right? Additive,
yes, yeah, that is my point.
Yes, but when you want to use this information to predict the breeding value for the next generation, so we often do not use the dominant estimation because, yeah, that's the part that cannot be accurately predicted. So we only use the additive part to do the prediction for the next generation. You can estimate the dominance effect within the F2 population, right? Of course.
Yes.
Yeah, but you cannot use that to make the prediction for the next generation.
Oh, okay, understand. Thank you.
Sure. All right, so this, yeah, actually this question is kind of very, very complicated. Yeah, I will not use this question like in this topic in the final exam. Okay. Any questions for this one? All right, so in what situation do we need to use EM algorithm to test whether, whether a locus is a QTL?
For missing data, right?
Yeah, yes, very good. Okay, so now, so I will ask you to very briefly describe how an EM algorithm works. So you just follow the lecture notes and describe the steps, the major steps that we follow in the EM algorithm procedure. So any questions here? And what is the difference between the regular MLE method and the EM algorithm?
MLE uses all the data, but EM also includes the missing data to guess the parameters.
Yes, very good. So once we have the complete data, so we can easily get the MLE, right? But if we have some missing data, we can still use MLE, but we have to assume the missing data is known. So how do we do that? So we can do the iterative analysis. In each step, we can replace the missing data by its expectation, right? Yeah, this is the strategy. And in the EM algorithm, so we still use the MLE by assuming the data is complete. But before we can do that, we just replace the missing value by its expected value. So that's the difference. Any questions here? Oops. Okay. All right. So this is the last question is the 3-point analysis. Okay. So Markov chain, right? So we have 3 loci on the chromosome like this, and so the simplest situation is for the backcross design. And so if this is a backcross design, so how many genotypes do we have for each locus?
2.
2, yes. The backcross, right? We have either 1 or 2, right? So A1 is 1 and A1A2 is 2. Okay, and we use so suppose at locus A, if the genotype is A1, we can say A equals to 1. If the genotype for locus A is in another progeny is A1A2, we say A equals 2. So the probability of them is both equal to 1/2. Does that make sense? Does that make sense to you, this?
Yes.
Okay.
Yes.
All right, very good. All right, now, okay, so the first question is to ask you to define the probability transition matrix, the T transition matrix, TAB. All right, so if there's no crossing over, so suppose, so you always see the A equals to 1 is linked with the B equals to 1, right? Because of the crossing over between this two loci. So you in some progeny you're gonna see the recombinants. Is that right? So then, so we need to calculate that matrix. So let me show you. So I don't think I can draw anything on this. Oh, okay, sure. So Ginny left the meeting because, so yeah, it's good to record this, and then so if someone has to leave the meeting earlier, so I can send a record, yeah, to everybody. Okay, sure. Let me show you this. Okay, so for the last problem, this is its transition matrix. You need to describe, right? You need to make a transition matrix like this. And because we knew the recombination frequency or the genetic distance between A and B is equal to RAB, then you need to write down a transition matrix for A and B like this. Is that clear?
Yes.
Now, why do
You
we
can
have to
do the same thing.
way?
Yes, for B and C, right? Go ahead, Ryan, you have a question?
Why do we have to draw it that specific way? Because there's so many different iterations that we see here.
Say that again, I'm sorry?
There's different way. We see it in so many different ways here. So why this way?
Oh, why this way? You mean why this way?
Mm-hmm.
Okay, so this is a, so let's say this is a backcross design, right? Okay, so backcross design means what? Means this. So we start from one parent, which is A1, A1, A1. Oh, I'm sorry, B1, C1. Okay, homozygous. A1.
Would it be wrong to answer with the transmission matrix AB equating to the probability of B being equal to 1 given A is equal to 1? And then would that be
again? So I didn't get your question. Sorry, say that again. You mean here?
Yeah. What if we use that matrix instead as our answer? Would we be incorrect, yes or no?
Oh, okay. But when we look at our, I think you can get partial credit. So because, let me see. Because I have specified the recombination frequency between A and B is RAB. So you have to use this. See that?
Oh, so
yes, you have to use this to express the entries in the matrix. So if I say, okay, we already knew the recombination frequency between A and B, and if we already knew the genetic distance between A and B, then please use this RAB to make a transition matrix, and that would be the final answer. So if you just use the first one as your answer, so Hmm. Okay, so I think, yeah, it's fine. So, okay, don't worry. So if you use this, so, okay, I think your question, I understood. I think I got your question. So if you use this part as your answer, yeah, that'd be fine. You can
Yeah,
still get the full credit.
that was my question because, mathematically that is valid. And so I was wondering, if we had a slightly different version from what you had in mind, if you would still be able to pick up on it and understand.
Yeah, so if you write down this, that means like you already got the point. I know you understand this, then you can get the full score. Okay, sure. Yeah, no problem.
Thank you.
Sure. So, okay. Okay, so this is the first part. So I just ask you to make a transition matrix for me. Any questions here? And the second one, okay, that's a little bit complicated. So here we are dealing with 3 loci, right? We have A loci, locus B, locus B, and locus C. And for this progeny, for this specific progeny, we observe that the genotype for A equals to 1, but the genotype for B and C equals to 2. So how do you calculate the joint probability of seeing this progeny, the genotype for this progeny, using the transition matrix A and B and the transition matrix B and C? All right, any questions here? Any problems? Okay, let me go back to this. All right, something like this. Does that make sense? The probability of A equals to 1, B equals to 2, and C equals to 2 should be expressed using this formula and this. So why there's a 1/2 in front of this two probability?
Because the genotype of A doesn't depend on, there's no flanking marker, so it's just on its own.
Right. So that's the start of the Markov chain, right? So it doesn't depend on anything. So we assume the probability of seeing any genotype is equal to 1/2. Very good. And then when given the genotype at locus A, then we need to calculate what's the probability that you're going to see a genotype equal to 2 for B, right? Then we need to use the transition matrix and so on. So once you got the B, so you need to calculate what's the probability you're going to see a genotype for C, right? Make sense? Yeah, so generally this is the level of the easiness for the final exam. So if you feel good about this practice test, then take it easy. You will feel good for the final, real final. So yeah, I think I'm right. I spent like a little bit more than 30 minutes to go over the practice test. All right, so do you have any questions about this practice test?
I have one, Dr.
Yeah.
Zhang. Could you go to the second problem?
The second one.
Second question.
Yes.
I'm still a little confused with the first question of problem 2. Cause for the backcross design, actually in the class you mentioned 2 different coding for the A1, A2, and A1, right? So one is use 1 to code A1, and 0 to code A1, A2. And the other one is use 1 to code A1, and -1 to represent A1, A2. There are 2 different ways,
yes.
right? But if we use the 1 to represent A1, A1, 0 to represent A1, A2. And the variance of Z should be, I think it's 1 over 4. But if we use 1 to represent A1, A1, and -1 to represent A1, A2, the variance of Z is equal to 1. So they are, these
Okay,
two
so
variances
yeah,
are different.
That's a good point. Thank you for bringing this up. So in this case, we try to be consistent. So for example, so let's treat them equally. So 4 different population, right? Backcross, F2, real, and DH. So let's use the uniform coding strategy for them. So for example, if we use, let's say F2, we have like -1, 0, and 1, right? For the 3 genotypes. And for backcross, you only see 2 out of those 3 genotypes. Just use the same coding. For example, 1, 0, or -1, 0, that's fine.
Okay.
And for DH and the real, we're still consistent in it regarding the coding, right? So because we only have the 2 homozygous, so you use the -1 and 1.
Okay. Yeah, understand.
Good.
And for problem 3.
Problem 3.
Yeah, so here, if we want to use the dominance model, does it necessary our population is a F2 like population?
Oh yeah, sure.
So at here, it's asking write down the linear model for testing additive effect and dominance effect. So here the population is a F2 population.
That's right. So if so even I didn't say that, but yeah, if you see that, so that means like that's an indication. Yeah, we are talking about the F2 population. Yes.
Okay. Thank you.
Sure. Any other questions? Or if you have any questions not related to the problems in the practice test, so we can still talk about that. Any other questions? Do you have any things unclear for the lecture? So we can go over. Yeah, we can spend a little bit of time here. Yeah, to go over that. Anything you want to discuss?
Not right now. But, I got too much on my plate right now. I'm in 24 hours maybe. But
yeah, take it easy. So no, don't worry. So because let me see. So we have how many days? Tomorrow?
About 3 or 4 days.
Huh?
About 3 or 4 days. So I have time.
Oh, sure. Anytime. So before the final exam. So if you have any question, just shoot me an email. So yeah, so either for simple question, I can simply answer your question by email, or if it's not that easy, so we can have another meeting. So individual meeting to talk about your question. Yeah. So this is nice because we have a very small class. I can handle students' question in this way. Otherwise, like in spring quarter, I'm going to teach a 250 students class, genetics. So yeah, I cannot answer a student question in this way. So I have to group discussion to answer questions. But yeah, in our class, yeah. So whenever you have question, if you want to have a discussion, let me know. So we can have a Zoom discussion.
All right. I'll take you up on that later on.
Sure. Okay.
All right. I got to get going. I have another class to TA.
Okay. Good luck. See you. Bye-bye. Any other questions? No? Good. All right. Very good. Thank you all. And oh yeah, right. So I think tomorrow is the last day for evaluation. So if you haven't done that, please, help me and so help me know well I can improve for the future class. Okay, thank you very much. All right, bye bye for now.
Thank you.
Thank you. Bye bye.